Alright, I have everything set up. So this is just a log of me trying to implement the 2013 paper by DeepMind where they play Atari with by using deep Q networks. So I have never actually looked at reinforcement learning. I mean, I know the concepts, but not really familiar with the math or any of the state of the art, etc. But let's see. It shouldn't be that difficult to follow through at least the paper, and let's see how far I go in one sitting. So the paper is basically, I think, playing Atari with deep reinforcement learning or something. I can just open up the paper. So yeah, and I won't be implementing all the games in this. So the point of the paper is that they learn a few Atari games, and I'll be doing it for Enduro, as you can see the title is already here. So let's call this playing Enduro with deep reinforcement learning, and I will just maintain a log here of the things that I learned while making this video, and maybe like, yeah, okay, first let's go for the log. Yeah, so yeah, this is the log. I have to keep remembering to switch windows because I'm recording on another desktop, so I mean on another monitor. So right, okay, let's go to the paper now. I did look at the paper before though. Some very big names: Silver, Alex Braves, and I have no clue what's going on with the indentation here. Just yeah, I'm OCD about this stuff. Back when DeepMind was still called DeepMind Technologies. This was the paper, as far as I remember, that put the company on the map. But let's just read. So we present the first deep learning model to successfully learn control policies directly from high-dimensional sensory input. The model is a ConNet trained with a variant of Q learning, so I have to figure out what this is. Input is raw pixels, okay? Output is a value function estimating future rewards. Okay, so the output is a reward sort of thing, and the input is just raw pixels of the game. So we apply a method to 7 Atari games from the arcade learning environment with no adjustment, okay? So they don't change the architecture for any of the games. They just run one neural network on all of them. And it outperforms all previous approaches on 6 wow, okay, so passes a human expert on 3 of them. Okay, these are the results. Shall I make this bigger? I'm not sure if it's this way. The upper table compares average total reward by running an epsilon greedy policy. So epsilon greedy is a variant of greedy. This is mostly used in dynamic programming approaches where you, instead of choosing the most optimal choice, you randomly choose a few times something that's not optimal in the hope that you find something new. So whereas if you always choose the best path, you're always going to stick to optimal path, but sometimes you might want to do some exploration. So that's what epsilon greedy is. I hope I'm not like too wrong. With epsilon is equal to 0.05. The lower table reports results the single best performing episode for H8. Okay, these are probably like some other benchmarks, but I think what we have to focus on is DQN, which is this, which they bolded. So breakout is 168 versus human 31. Enduro is what we care about. Humans are very good at Enduro apparently. 368 versus 470. So our goal will be to basically match these numbers. I'm not sure if we'll get to 470 because who knows what compute they work with, etc. But should be able to beat humans. Like if this paper is good, which it is, it's a seminal paper. And I have no clue what's happening in Pong. Why is everyone losing in Pong except the DQN? Even the human lost. Pong is like the table tennis sort of thing, right? Okay, so I mean, I understand what the paper is doing from a very, very high level. It takes in raw pixels, it uses a ConNet to get features, and then the features are fed into probably some sort of linear layer, etc., to get a bunch of rewards. And then maybe the training of those rewards, maybe the training of the neural network is done by what do you call it, like using whatever they call this Q learning is. So introduction, I don't want to read all this. Maybe I do. Just skimming super fast. Okay, this paper demonstrates that a ConNet can overcome whatever challenges to learn control policies. What on earth is a control policy? From raw video data in complex RL environments. I have no clue what a control policy is. The network is trained with a variant of the Q-learning, blah, 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 blah. Stochastic gradient descent update the weights to alleviate the problems of correlated data and non-stationary distributions. We use an experience replay mechanism which randomly samples previous transitions and thereby smooths the training distribution over many past behaviors. Okay, this is super complex. To alleviate the problems of correlated data and non-stationary distributions. I wonder what a non-stationary distribution is. What is a non-stationary distribution? Like random walks. Fair. Okay, so this is almost like some sort of Markov process, huh? Okay, fine. To alleviate the problems of correlated data. So correlated data usually means that the data is not IID, which in neural networks you really want. You make an assumption that your data is IID. So they're saying that the data is correlated, yes, but why is it correlated? So you have a racing car online. Let's play Enduro. Okay. So how do I play? Is it left, right? Instructions. Game reset. F12 to start the game. Arrow keys to move and spacebar to fire. Okay, do I need to? I don't. Okay, wait. F12 and go. Okay, so left and right. Fair. Okay, these cars are overtaking me. So I hit spacebar and okay, nice. I wonder how far I will get in this game. I know it's not the point of the video, but I started playing, so this is what you call distraction. It's not straightforward to play this game. So I see that the counter's counting down. Okay, straight again. I'm probably good. Oops. Oh, so you can't hit the car, huh? That makes sense. So you hit the car and you're penalized. Oh, what is this? Whoa. Okay, so you have like changing environments. You have like snowfall, you have grass, and you have like curved roads as well, which is super complicated. So I can hit left, right, up. I can even slow down. Okay, that was not intentional, but oops. I can even slow down like I did just now. I don't want to get overtaken. Whoa. Okay. I'm really horrible at this game. I think the game started at 200 and I'm at 50. I have no clue how the human got to 370. Whoa, 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 whoa. And full disclosure, I'm horrible at video games. I've never played them, and in general, I think they're a waste of time. But, ooh, okay. Whoa, whoa, whoa. Okay, I get the point. So I have down, up, left, all these functions, and I just need to go as fast, and I just need to overtake as many cars as possible. That's the point, right? Whoa, that was so cool. Did you see that? Okay. So, okay, I get the point of the game. Why did I go to the game? Right, correlated data. Why do they think that the data is correlated? The only explanation I can think of is that, let's say you get a frame as input, and you learn, let's say you have the best reinforcement learning algorithm ever, and then you, what do you call it? And then you get the best, let's say the perfect button to press, like left, right, space, whatever. And the immediate next frame is like a carbon copy of the current frame, apart from like maybe like a little bit of difference. So in that sense, a lot of successive frames are literally the same frames. So you're trying to learn a many-to-one problem, which is never going to work. So the IID assumption fails in reinforcement learning. Okay, is that it? We use an experience replay, which okay, oh yeah, that makes sense. So now, so to solve that, they randomly sample from previous, whatever this means. So I'm assuming they randomly sample from previous encountered frames instead of the immediate one after the other, so that they, yeah, okay, I mean, I just had to think, okay, go through the whole thing, and thereby smooth the training distribution. Okay, that makes a lot of sense. We apply our approach to a range of Atari games implemented in the arcade learning environment. So that one I already found. It is this nice repository. I was trying to check if the code would work on Colab, so I had to look at this repository beforehand. And it does, so this is all you need to do to get an environment in, sorry for the sound, this is all you need to do to get the environment working. It's fairly nice, so I'll just, not right now, but maybe like once we finish going to the paper, at least the first glance. Okay, faster. So, God, sound is horrible. Right, so our goal is to create a single neural network agent, blah, 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 blah. Okay, fair. So this is the input size, I'm assuming, 210 cross 160. Fine. We consider task emission agent interacts with an environment, okay, in this case the Atari emulator. In a sequence of actions, observations, and rewards. Okay, at each time step, the agent selects an action from a set of legal game actions. Okay, that's nice. The action is passed to the emulator and modifies its internal state and the game score. The emulator's internal state is not observed by the agent. Instead, oh, okay, fine. It gets the image, okay, from the emulator, which is a vector of raw pixel values representing the current screen. Yes, I understand that. In addition, it receives a reward. Okay, fair. Since the agent only observes images, the task is partially observed. Many emulator states are perceptually aliased. Okay, it is impossible. Fine. Why are they writing the same thing two times? We therefore consider sequences of actions and observations and learn the end strategy. Okay, all sequences are assumed. This formalism gives right. Okay, you know what? This is super technical. What I'm going to do actually is go and open my copy of Sutton and Bartow. So, wait a second. Yep. Yeah, there we go. Such a beautiful cover, but just zoom in. Oh wait, where is the summary? No, where are the contents? Okay. Reinforcement learning, I don't want to read all this. Right, Markov decision processes. Okay, nice. So let's just see if we can understand anything. If we can't, I'm just going to stop recording and sit and study. But, so this is the agent, it gives an action, gets a reward in a state. Fair. More specifically, okay. Okay, so there's a sequence. No, that's what they mean by sequence. Okay, right. So the sequence that is talked about in the paper is, where is that? Yeah, so we therefore consider sequences of actions and observations. X1, A1, I don't know where the reward thing is here, but yep, I realize that that's what they mean. Now going back to the book, okay, so there's like the state and the action and the next, and the reward that's gained, and then the next state, the next action, and the reward after that. So in a finite Markov decision process, so okay, so I understand why it's called Markov process because it's memoryless. Once you're in the next state, it doesn't matter where you came from. And maybe it's called a decision because you pick an action, and process is self-explanatory. Right, so in a finite MDP, the sets are all finite, right, obviously. In this case, the random variables have well-defined discrete probability distributions depending, yep, that makes a lot of sense. So the probability of a reward is, depending only on the preceding state in action and the probability of the next state as well. So I think that's what's written in equation 3.2. So the probability of S dash, which I think is the next state, and the reward given this state and this action is this probability. Yep, okay, that makes much more sense. Obviously the sum overall is just 1 because it's a distribution. And then, okay, all this is not necessary. Examples, okay, goals and rewards. Okay, so let's see what this. In general, we seek to maximize expected return, denoted GT, which is just the sum of all the rewards after that time step. So GT is reward of t plus 1. Okay, so when you're in a particular state, you want to maximize the return in that state, and the return in that state is just, let's say if you're like a perfect agent, what would be your, what would be like the reward that you accumulate from now till the end? Yeah, so that's what this means, right? T is the final time step. Okay, that's also very intuitive. Until now, this book is like super nice, much better than the paper. Then, What is this? The additional concept we need is of discounting. According to this approach, agent tries to select actions so the sum of discounted rewards it receives over the future is maximized. In particular, it chooses 80 to maximize the expected discounted return. Okay, so this is like a geometric, okay, not really, but yeah, so you just multiply it with a factor of less than 1. So when time goes to infinity, this, okay, the rewards at time infinity is basically 0. That's what it means. Okay. Right, if gamma is 0, then agent is myopic. It's like greedy almost. If gamma is 1, then it's like, it's the best case scenario, right? Ish, something like that. So GT is RT plus, okay, this is just some notational nonsense. I don't want to see, what is this pole balance? I've seen these videos on the internet. Unified notation for episodic and continuing tasks. So my strategy while reading this book is to just go wherever there is a nice math formula and try and understand that. So everything else I'll just infer because speed is of the essence. So what is going on here? At t plus 1, this is just gamma of 0. Oh, so that's what they mean by unified notation. So it doesn't matter what t is, whether t is infinity or t is finite. Yeah, that's literally what they're written here. I mean, I don't have to talk. Including the possibility that t is, yeah, whatever. Policies and value functions. Oh, this is what it means, huh? The policy stuff. Let's read this carefully. Involve estimating value functions. Okay, so value functions are, they estimate how good it is for an agent to be in a given state. That's nice. Okay, fine. Formally, a policy is a mapping from states probabilities of selecting each possible. Okay, so it's like, what is your policy right now? Like, what is your plan next? That's all. So pi of a given s is just given in a state as what action will you choose. This is turning out to be remarkably more simple than I expected it to be. What is this? Okay, the value function of a state s under a policy pi is the expected return when starting in s and following pi. Okay, expected return gt when you're in this state. Okay, and this is expanded form of gt. Okay, much ado for nothing. What is q? Similarly, we define the value of taking action a in state s. Isn't that the same as this? Oh, there's no action here. Okay, so this is like a one dimension extra on top of the state dimension. So not only do you have to be in a state, but you also want to define like a reward for each particular action. Okay, that is also understandable. Expected return. This is again just the expanded form of it. Very, very nice. What is this here? A fundamental property of value functions used throughout RL and dynamic programming is that they satisfy recursive relations similar to that which we have already established for the return. What did we do? Okay, so basically, like you can take the current reward out and apply the exact same formula to the rest. That's what the recursive relation means. For any policy pi in any state s, the following consistency condition holds between the value of s and the value of its possible successive states. This we already seen. This also. This is from this 3.9. And whoa, what on earth is this expansion? So I know what is happening here. This is just linearity of expectation. You know, this is the exact same thing as this, but removed. But RT plus 1 is removed. And okay, so sum over all states, all rewards, given a particular state in action. And then you sum over all actions. Oh, so this is literally like what do you call it? Like a brute force iteration where you just go to every single possibility. Isn't that it? So this is like a sum over all possibilities of all states, all actions, and all the rewards that you can get. So that's what this means. Let's read. Okay, note how in the last equation you managed to blah, 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 blah. Note how the final expression can be read easily as an expected value. It's not that easy, but okay. It is really a sum over all values. Yep, yeah, that's what I'm saying. For each triple, we compute its probability and weight the quantity. Okay, very good. Equation 3.14 is the Bellman equation for B pi. What on earth is the Bellman equation? Okay, whatever, none of my business. Let's call it the Bellman equation. Yeah, so this is like the recursive tree. Oh, that's where it comes from, huh? So it's literally a dynamic programming approach. Fair. Okay, optimal policies and optimal value functions. Okay. For finite MDPs, we can precisely define an optimal policy in the following way. Okay, makes sense. Okay, so they're just saying there is an optimal value function. Yeah. This is, I love how this is written more like a pure math book rather than a computer science book. Because this is the kind of stuff you would only see in like some, Russian rigorous math book where there are a bunch of numbers and we define one number to be the maximum of all those numbers. So, anyway. What is this? Okay, right, fair. Yeah, this is the exact same thing again. Okay, wait, what? Is there anything important here? Max of this is max of this is max of this, okay? Max of this is also right. Ooh, what? How did 3.19 become 3.20? Expectation of... oh, okay, so max over A has been just sent inside. Okay, so this is again like this recursive equation. So what is happening here is you just send the maximum of A and you call it A dash, which is the next action that you'll take. So you go to the next state and then you just greedily pick the best action from there and you add it to the current state action value function. And by this, you will obviously converge at the best solution because of so many reasons. But the simplest reason is that let's say you get rewards of RT plus 1, RT plus 2, RT plus 3, so on and so forth until R capital T, where capital T is the final step. You can write an inequality where each of these is less than the maximum reward. Each of these individual terms is less than the maximum reward. And so therefore it is guaranteed that this sort of thing is going to converge to the best return. So this stuff is like super common in like most dynamic programming approaches. So, okay, optimality and approximation. Fine, this is summary. Okay, nice. Dynamic programming. Should we go to this stuff? Policy improvement, policy iteration, value iteration. Let's just go to Q learning. I think we've done enough. Let's see what. I recognize these terms, RT plus 1, gamma. I know, I get this. This is just optimal Q value function But what exactly is this stuff? What is TD learning? TD. Oh, is it temporal difference? Oh, nice. Temporal difference learning. Yes, this is just like 1 minus alpha times x plus alpha times x or something like that, right? No, 1 minus alpha times something plus alpha times the other thing. Isn't this just like a linear sort of? Yeah, it is. Why did he write it like this? This is so weird. I've never seen it written like this. This is the linear update rule. So this is 1 minus alpha times VST plus alpha times GT. It's, I mean, okay, maybe this is like what happens in other literature, but yeah. Okay, we've seen on this stuff. Okay, so GT is just expanded into this and written like this. So this is basically, what is this? The policy, okay. Parameter step size, okay. Initialize everything arbitrarily except we have terminal. What is terminal? Okay, the final state maybe. Fine. Loop for each episode. Initialize S. What does initialize S mean? Does this mean choose a starting S? Because isn't S like a set of states? What does it mean to initialize it? Anyway, loop for each step of episode. Take an action given by the policy. Take the action. Observe the reward in the next state. Update this. Okay, fine. So for some reason this works, is what they're saying. Advantages of TD prediction methods. They don't require a model of the environment. They're naturally implemented in online, fully incremental fashion. Yeah, I mean, I think it goes back to what I was saying. You keep doing this, and because of the fact that it will definitely converge, it might take like ages, but it's guaranteed that your algorithm will converge. So, yeah, so see, if they both converge asymptotically, so it's like proven that they will converge asymptotically to the correct prediction. So apparently Monte Carlo methods are like, right, so Monte Carlo methods probably use more randomness, whereas temporal difference methods are like just, okay, we're just going to go keep, chopping at the block, and we'll get there. Optimality. Okay, there's no math here, so I'm not going to read all this. On policy TD. What is on policy? Fall into two main classes: on policy and off policy. Isn't this the exact same thing as this? What is the difference? Q. What is the difference between this and this? There's a max here, and there's no max here. Wait, let's just read the pseudocode. Step size alpha and small epsilon. What is epsilon? Okay, for the epsilon greedy. Okay, fine. Initialize this except the Q terminal. But here you have also an action, so that's the dot. Initialize this. Again, this is bugging me so much. What is the meaning of initialize S? Whatever. Choose A from S. Even if they said like select an S or something, I would have been fine. Initialize means you're going to like whatever. Choose A from S using policy derived from Q. What? But you don't have a policy. Okay, so it's right. Okay, that was just brain fade from me. But right, whatever. Using policy derived from Q, okay. Loop for each step of the episode, which is the exact same thing, and choose another A using the policy. Oh, I know what the difference is now. So here you don't have a choice. You have to choose the best possible action, which is what max of A means, max over A means. Whereas here you're given a choice. Like using an epsilon greedy paradigm, just choose randomly sometimes or max sometimes. So that's probably the difference. Right. Yeah, that's the only difference I can think of. What I don't understand is what exactly is the meaning of off policy. Is it not written anywhere? Whoa, it's an exercise. Why is Q learning considered to be an off policy? But tell me what off policy is first. Off policy. So you have a policy and you don't follow it? Is that what it means? Oh, right, that's what it means. So whereas this is on policy, which means you have a policy and you're going to choose A from that policy. Okay. Whereas here you choose the maximum A no matter what your policy is. This could be like anything. This could be like choose the worst option, but you would still have to. Okay, fine. I get what Q learning does now, thankfully. Let's go back to the paper. This is the return. We know what this is now. We know what this is also. We know what the Bellman equation is also. The basic idea is to estimate action value, right? Using this, yeah, we know this. In practice, this approach is totally impractical. What a line. In practice, this approach is totally impractical. Because the action value function is estimated separately without any generalization. Instead, it is common to use a function approximator to estimate the action value function. I actually figured it out now. So what they're doing is they're just using a neural network to approximate this Q value instead of computing it using like some sort of tabular approach, something where you have a pair of states and actions and you write down the values. In the reinforcement learning community, this is typically a linear function, but sometimes a non-linear function approximation is used, such as a neural network. And here, this is a content in this paper. Fair. And the loss is literally just the true value minus the Q value. But how do they know the true value? Is the target for iteration I? Parameters are held fixed on optimizing loss function. Note that the targets depend on network weights. Isn't the contrast which are fixed? Yes, exactly. Okay, so you just take the targets from the previous network weights. You don't mind. Oh, this is so clever. It's a wonder that this works. Differentiating the loss function with respect to the weights, we arrive at the following gradient. Okay. It's been a long time since I've actually seen a differentiation in a deep learning paper. Rather than computing the full expectation, it is often computationally expedient to optimize the loss function by using SGD. Okay, whatever. Here I find out that my idea was right. So off policy literally means that it follows a greedy strategy while it's, yeah, okay. Nice. Related work, none of my business. Deep reinforcement learning. This we've seen this from the book. In contrast, experience replay where we store agents. What is going on here? In contrast to TD Gammon, we utilize a technique known as experience replay, where we store the agent's experiences at each time step in a dataset D. So they store the state, the action, the reward, and the next state. Okay. Pooled over many episodes into replay memory. During the interval of the algorithm, we apply Q-learning updates to samples of experience drawn at random. After performing experience replay, the agent selects and executes an action. Since using histories of arbitrary length as inputs can be difficult, a Q function instead works on fixed length representation of histories. Let's just read this pseudocode. Okay. Initialize replay memory. And they say they do that by just... Okay, so they play the game a bunch of times, and they take these experiences, this tuple of the current state, the current action, the reward, and the next state, and they fill it. So that's what this means. Initialize action value function Q with random weights. That makes sense. That just means like initialize neural net. For episodes 1 to M, to initialize the sequence and pre-processed sequence. What does pre-processed sequence mean? Yeah, I mean, I saw that. It says, since using histories of arbitrary length, a Q function instead works on fixed length representations of histories. Is it written anywhere else? Okay, let's assume that this is what they work with. Okay, with probably epsilon select, this is just epsilon greedy. Otherwise, select this, execute action, observe reward, blah 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 blah, and pre-process. See again, I have to figure out what this is. Store the transition in the replay memory. Sample random mini batch of transitions from the replay memory, and oh, okay, I understood what the replay memory thing is now, or the experience replay thing is now. Okay, I get it. So you have a bunch of gameplay sequences in the replay memory, and when you're learning, what you're going to do is you're going to take a bunch of random stuff from the replay memory, and you're going to set. Okay, so this is very clever. So instead of starting off with like a bare bones neural network, just play some games, see what happens, and use that. It's sort of a different kind of initialization where you're already initializing it with some sort of good weights, if that makes sense. Second, learning directly from consecutive. I figured this out. Yep, this is what I was talking about before. Due to strong correlation. See, this consecutive samples part is the problem. Randomizing the samples breaks these correlations. Okay, nice. Third, when learning on policy, the current parameter determine the next data sample. For example, the maximizing actions to move left, then the training samples will be dominated by samples on the left hand side. The maximizing actions which is the right. Okay. Yeah, this is literally the whole IID thing. By using experience replay, this is averaged. Fair. In practice, our algorithm only stores the last n. Samples uniform. Okay, so you would need some kind of queue, right, to store this. So you store like n, and then the next time you add something in, you have to remove whatever's been done before. Yeah, I can tell that I'm going to implement this because I'm already thinking of code. So, right, this approach is in some respects limited since the memory buffer does not differentiate important transitions. Blah 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 blah. Similarly, the uniform sampling is equal. Right. More. So this is like a next paper idea sort of thing. Pre-processing and model architecture. Okay. 128 color palette, computationally demanding. Okay, first I convert it to grayscale, then resample to 84. Okay. GPU implementation requires square inputs. This is like 12 years ago. For the experiments, the function phi applies this pre-processing to the last frames. Oh, so you just take 4 frames, do the pre-processing. That's what it means here. This phi stuff. Okay, now this is a connet. Yeah, this is just what has been done in the past. This paragraph, so I just skip. There are 16 filters, 8 strike 4. And then 32. Yeah, this stuff we can do by ourselves. It's not like super important. Experiments, blah 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 blah. I just have to know these things. Mini batch size 32. Epsilon greedy 1 to 0.1 over the first million frames and fix it 0.1 thereafter. We train for a total of 10 million frames. Okay, that is going to require a lot of RAM. So 84 times 10 power 7. So that's like 10 power 8, 9, 10 already. So that's like gigabytes we're talking about. And then if I store it as float 32, there's no way I'm going to work. If I store it as, I think I need to store it as like unsigned int or something. Uint date, probably. Yeah, 10 million frames is not possible. How is that even possible? I mean, at least like with human compute. Okay, what is this? We also use frame skipping. More precisely, the agent sees and selects actions. Why? Since running the emulator forward for one step requires much less computation than having the agent select an action. This is very clever. They skip frames for each, so that you can run like 4 agents instead of 1 at once. I like these sort of fine details. Training and stability. Okay, and this is going too far ahead now. Conclusion. Is there an appendix? No. Oh, there's a Neuralist paper, so it's 8 pages long. So yeah, I get what to do now. Let's right. How long have I been talking already? Oh god, it's been 45 minutes. So let's go and write some code. Give me 1 second. Alright, I'm just checking something else. So here, log, what have we learned already? So we know what Markov decision process is. Is that even right spelling, or is it? Right. So this is memoryless, and you basically choose an action. And you get like S0, A0, and then R1, and then similarly S1, A1, and R2. So this is how you, let's put this in code so it looks nice. So this is what you get as a sequence. What else did we read about? Returns, and specifically discounted returns. Then I can't think of, yeah, then we did value functions. First one was just state value function, which was like v pi of s, and I have no clue why this isn't rendering, but it should. No? Okay. Why is latex not rendering? Whatever. And then state action value function. So this was basically q under a policy pi, and it had both state and action. So is it because of the bullets? Yeah. Huh, very interesting. Very interesting, no? Anyways, after this we went to, I know now what a policy is, and Bellman equations, then let's remember, I don't want to look at the book. Yeah, optimal value functions. Then we went to temporal difference learning. Then we did on policy versus off policy control is what it was called, and then we did Q learning, and then we did function approximators for Q values, and experience replay, frame skipping. Then what else? Yeah, there was that frame stacking and pre-processing. Then yeah, that I think that's it. So yeah, this was all we learned from the paper. Now now we just write some code. So import torch, then what else is there? Then obviously NL functional. Oops. Let's import numpy for good measure, and to work with images. Then right, yeah, so this should do the trick. Alright, and then I also need to get this stuff, which is ALE. So to do that, I will go back to my browser and just go import Gymnasium as gym and import ALE.py. Okay. Nice. Is there anything else I need? Should do the trick. So device is just, is it torch.coda.is is available. Okay, and then I'll just print device to see what we're on. So I'm not going to be like using yeah, so right now it's not connected to GPU, but maybe later, because you know I don't want to give up on my computer right away. So let's run this, and while it runs I'm going to think about what I need to do first here. So what do I need to start off with? I will need to have like what happened here? Oh, this is capital I. Come on, not a good start. So here I will start off with the training loop, and I'll call it train here. Okay, so now we start thinking. Obviously, first thing I need is the environment, right? Everything is downstream of getting the environment. So let's just get that first. Okay, I need to go back to the code there. So environment, I just need to do gym.make, okay? And okay, fine. So I get like the observation, the reward, whether it's terminated, truncated, okay, fine. And then some info. Alright, that is pretty understandable. So env is equal to gym.make, and ALE Enduro v5 is the name. And let's see, what was that again? How do I find out what is the number of actions? What is the number of actions? How do I find that out? Basically, I want to print action space. Okay, nice. So just 9. Okay, nice. So do I have like a dot item or something for this? Dot contains. No, I want like a dot item. No. Let me just quickly search. So it's probably not visible on the screen because it's, I've opened another browser, but yeah. Okay, so .n works apparently. Nice. Alright. Next, what we need to do is, I'll just print this out in a much nicer way. So the environment and the action space has this many actions. Okay, this is a good start. But what I still want to do is get some sort of ops info is equal to n dot reset. Okay, so this is like some numpy array, huh? Nice, okay. So I get number of lives. Okay, what? Fine. Episode frame number and frame number. Okay, that's, yeah, I mean, I get how to work with this. So what I do need is, I need an agent, right? So let's first write an agent. This is going to be class dqn agent. And yeah, I'm just thinking what sort of stuff to put in here. Obviously there is then what else do I need? I will need for sure, so the agent needs to select an action from the environment or from the space of actions, so maybe that also. Then, and then after that the agent has to sort of, what do you call it, it has to optimize the model, let's say. Okay, B. And what do we initialize this agent with? What are the stuff that we need this agent to have? Obviously we need the input, which is the size of the 5, you know, which is 84 plus 84 plus 4. So let's say we call that the state shape. Oops. That is the input. And we need the number, the output, which is the, you know, the number of actions. So let's call that action dimensions. It's the exact same as number of actions. And we will need like step size, so maybe like learning rate. Then we will need the discount, which is gamma. Then we will need, what else do we need? Obviously device, because we're going to be running this on both, I mean, either on CPU or GPU. So this seems good for now. So let's go around. So self dot action dim is equal to action dim. Then what else? Oh, we also need epsilon, but it's like it goes from 1 to 0.1 and it is changed. Okay, I see some problems here. I think what I need to do is I need to have a hyperparameter cache here. Okay, and I need to fill it with a bunch of hyperparameters. So let's say gamma is equal to 0.99. I forgot what it was in the paper. Let's check. Experiments. Is the value of gamma written anywhere? It's probably not. Yeah, I'm just scanning quickly to see, because I thought I saw, maybe it was in the book. So, whatever, it's fine. Back to our code. And then we saw that batch size, obviously. Batch size was how much? 32 millibar size? Yes, that was it. And let's put learning rate equal to how much? Something like super small, maybe 0.00025 maybe. And then obviously the reason we came here was for this. So epsilon start is 1.0, epsilon end is 0.1, and how fast do we want this to decay? Epsilon decay. So we're going to be implementing like an exponential decay, and so the number of frames, right? How many frames do we want this to go? So let's say the total number of episodes, let's call this num episodes, is equal to 500, and let's put frame skip as well is equal to 4, and then the phi, the number of frames we stack, so stack size is also 4. So the epsilon decay, so there's like 500 episodes, so that around 500,000, little more than that, little more than 500,000 frames. So how do we want to do this? So let me have it at half of the number, so 250,000. That should do it. Then obviously one big thing is the buffer capacity of the replay buffer. So let's go and put this at, yeah, I know it said like 10 million, but I'm going to do 100k or 100,000, sorry. No, both of them are the same thing, aren't they? So, yeah. And one last thing for the replay buffer is I need to collect a bunch of frames initially, right? So I need to go, let's say the initial, that should be around, let's say 50k. Okay, this looks good. So we have a bunch of hyperparameters. I'm thinking if I'm missing anything, but if we have missed them, we'll come back and we'll just put them back in. So now we go back, we just run this. We go back to our DQ and agent, and we just add epsilon start, oops, epsilon end. What else? What else? What else? Yeah, and we also need to see when we have to update the network. That is one thing I completely forgot about. So we have to basically add another parameter here, like, which is like, let's say after every 10,000 frames. And then that is also something that we put here. Just thinking if I missed anything. So, and now, yeah, I think we got everything. So just I'll just fill these out quickly. Then what else? Nice. And obviously device, finally. Cool, cool. Okay. So we have all these hyperparameters. Now what we need to do is we need to initialize this network. And yep, and the next thing we need to do is initialize the network. So we need a policy network and a target network. And then we need to initialize the target network with the same weights as the policy network, so that when we set the target network to eval mode, we can just learn it off the target network. So right. So let's first have another function, another class, where this is like meat of the whole thing. Let's call this dqn. Oops. No, this is nn dot module. What happened here? Why is this an error? So every single network will have a number of actions as the output, and if it has that, it should be happy, right? So if it has that, it should be happy. I'm just thinking how to implement this now. So obviously I'll write the and then we need a bunch of conf layers here. So this one we can write whatever we want. So let's call this self.con1. Okay, so how many in channels do we want? So the in channels will be stack size, which is 4. This is always going to be 4. And the out is going to be, let's say, 32. And then kernel size, we saw was around 8ish. And then there was like a stride of 4. Now self.conf2 will take output from this. So this is going to be 32. And so should I just make this 64? 64, and then maybe the kernel size 4. So what I'm thinking is that, so this is 84, which is the input. So 84 minus 8, because 8 is the kernel size. 84 minus 8 is 76. 76 by 4, because the stride is 4, that is going to be 19. And then you add 1, which makes it 20. So the input right now, this is going to be like 20 by 20 times 32. So now I need to have, if I want this to be 64, what would happen is, let's say I have kernel size equal to 4. So 20 minus 4, 16 by 2, 8 plus 1, 9. So 9 by 9. And it's obviously like a stride of 2. So kernel size is equal to 4, stride is equal to 2, and this is going to be 64 times 9 times 9. Right. Then one last conf layer, conf2d, this time 64 comes in, and let's keep it at 64, kernel size. So this is 9, so I want an odd number like 3, then 6 by, let's say stride is just 1, and yeah, let's finish with 7 by 7. So this is going to be 6, I don't know why it's 62. 64 times 7 times 7. Now I need self.fc1, which is nn.linear. Okay, so what would be the input to this? So I could just multiply 64 times 7 times 7, but that is not ideal because in case there is a difference, you don't want to be stuck with a hard-coded value. It's always a bad idea to do that. So just very quickly, I'll have a conv output size. Let's call this get conv. And the input is going to be self and like a shape, so that I can just run a random array through it. So like a dummy is going to be like torch.zeros of so it has to be 1 and shape. Nice. And output is equal to f dot relu of on 1 of dummy, and then this stuff has to be self dot, and then output is equal to f dot relu of self dot conv 3o, and now I return the product. So np dot product of output of size. Did I not? Nice. Okay, so now it should. Where's this one? And let's just make this int for good measure, right? Because who knows what. Okay, now this is very nice. No matter what happens, I will always have a good. So I'll call this self dot feature size is equal to self dot get output size of shape. Here I just, what shape do I give it? The shape is stack size 84. This won't change, so I don't have to worry about this. Now I go to linear. Let's say this. So what is 64 times 7? 448. 448 times 7 is around 3049-ish, somewhere around that range. So yeah, this seems like a good. So self.fc2. Here this is going to be the final layer. This is going to be 512 times number of actions. Simple. And that's as simple as it gets. So let's like break it down. So the input is like 4, 84, 84. That goes to this, then this, then this. And the last thing obviously we need to do is write the forward function. And self, and what else? Let's call this x. So we just need to copy this stuff and change this to oops, no, x. It's so much harder coding on this stuff. And now we just flatten this, so x is equal to x dot view. Maybe we could also do reshape, but I for some reason like views. And the other one is just invert, so -1. Yep. And then we just do x equal to f dot relu. Now how do we apply yeah, should work. And then the final thing is you just return self dot fc2 of x. That's it. Nice. We have our deep Q neural network. And now we just need to use this stuff to initialize the policy and target networks. And yeah, that's it. Here I have to start with the initialization. First I will call a policy net, and I will call it with dqn num actions. What happened? dqn okay, yeah, action dimension, and I need to remember to send this to device. So like anytime you just you call a neural network, especially a .NN.module, just automatically send it to device, so you don't have to forget later and struggle. And then obviously target net is the same. Okay, we have a policy net, we have a target net. Now we have to set self.targetNet state dictionary to be the same as of the policy net. So we go policy net. I think the call is .static. Yep. And then we need to set self.targetnet.eval so that it's not learning, because we don't want the target net to learn it. And now for the fun stuff, self.optimizer, we use optim.rms, and our parameters are, so we're learning the policy net, right? So we just go policy net dot parameters, then our learning rate is our learning rate, and then let's set some other stuff. This is fairly straightforward neural network stuff. We don't need any regularization in this, so I'm just setting weight equal to 0. Then here the loss is nn.smooth L1 loss as written in the paper. Then and one last thing that we will keep count of is how many steps have been taken by the agent for log's sake. Right, there we go. What next? So shall I just start implementing select action? So select action takes in self and state, right? Because you're in a particular state, and when you're in a particular state, you first need to calculate the current epsilon threshold. So and the epsilon decays exponentially from EBS start to EBS end. So let's do that. So we start off with EBS start. No, we say self.eps end plus the difference between start and end. I hope that is correct. Let me think in my head while I'm typing. So to decay it exponentially, we need to take the ending 0.1, then find the difference between the start and the end, which is 1 minus 0.1, and then we need to multiply it with e power minus the steps that have been done divided by the number of steps at which we want to decay it. Right? So I just need to go into np.exp. Let's minus 1 times self.steps done divided by self.eps decay. Right? Yeah, this is it. And now, if let's generate a random number, if random is less than this, okay, did I not import random? Let's do it here. Nice. If random, why is it still bothering? Yeah, good. If random.random is less than this, we just return a random action. So it has to be a torch tensor. Let's fill this up first, and d type is equal to torch.float32. Wait, no, this has to be long, right? Because these are integers. Now, okay, how do you sample from this? So self.actionDim is 0 to 8. I just need random dot, yeah, okay. So I just need to go random dot rand range of, that's it. I'm just thinking if I missed anything. No. Then else. Now we're not learning anything, so we go torch.nograd. First we have to convert these states into PyTorch sensors. We have to convert these into, yeah, right. So torch.sensor state, and then d type is torch.float32 here, and we just unsqueeze to self.device, and then normalize all this. Then we get the Q values by just indexing from this, and we return these Q values. But we return the argmax, so we go Q values dot argmax, and first, and then we do it as 1,1 torch tensor, and it'll be done. So here what we're doing is we find the index along the first dimension, which is the action space, and then we just reshape it to 1,1 tensor and return it. This will now select an action. So it will. So if we notice what is happening here is if it is random, it just goes select something randomly. Otherwise, it chooses from the policy net, and it gets the first dimension, which is the action values, and then takes the argmax. Finally, we have to optimize this model somehow. I think this is where we will run into a big glitch. Until now, things have been pretty smooth. So, because here we will need the replay buffer, right? Because otherwise we can't optimize it. Okay, here we definitely need the replay buffer. So at least maybe we can just start off with initializing this stuff. So let's go back to our original training loop. So agent is equal to dqn agent, and bunch of state shape is equal to stack size 84. Then action dim is equal to number of actions. Then lr is equal to learning rate. What is next? Gamma. What is this? From RE import L. When did I type this? I know class can be. Name dqn agent. Oh, right. So I just need to run everything once. Yep. So what's happening here is the dqn agent has initialized itself. It has initialized 2 networks, and everything has happened. Now all that remains for me is to write the replay buffer, and then the pre-processing, and then the optimization. This will take a long while. So let's say replay buffer is oops, and I will call it with this. Now I just go back somewhere and I write this replay buffer, maybe here. Oops. That's all I need, right? I just need the total capacity of the then I need to push stuff to this. This is basically going to be a queue at this point. What do I need to push? I need to push the state. I need to push the action, the reward, and then I need to push the next state. And then I also need to check if it's the final state. So that, let's call it done. And then I need to get the length. Before that, I need to sample from the replay buffer. So let's say I have a batch size. I need to sample. Then I think the last, I should definitely want to give the length, but this is more like a, oops. And then here return self dot, oops, no. So yeah. And so here what I'm going to do is just set self dot buffer to be equal to this has to be a queue. So I just need to go back here and from collections import DQ. Nice. So here this has to be, that's it. We have initialization, and then for push, all we need to do is self.buffer.append, all these things. We need to make this a tuple first. So state, action, reward, next state, and done. And how do you sample? So I've pushed, I have a length. How do I sample? How should I sample from this? So I could just have like a bunch of, so I just do random.sample initially. So let's say I call these transitions. So I just call them random.samples, self.buffer, and then the batch size. From this, what I can do is, so for every single one, I can just have a, so, okay, but these are again long tensors. So I need to convert them to float 32 first. Okay, fine, so let's call these raw, actions, rewards, next states, raw, and then let's call them duns is equal to, so this will create like individual separate lists for each component instead of the list of all tuples. And now we will convert these into float 32s. So states is going to be torch.tensor. What do we need here? So this is first we convert to np.array to make things easier. And then we do d type is equal to torch, oops, float 32. Send these to device by 32, no, by 255. Copy, paste, next states. Yeah. Now we just make sure that all of these are the right types. So actions have to be long tensors. So np.array actions, this has to be d type equal to torch.long, and then send this to device. Okay. And rewards have to be float 32. They could be long as well, but best to have them as float 32. Oops. Then what is it? Done. Yeah, this is just boolean, so don't have to waste too much memory. And then I just return all these. Return states, actions, rewards, next states, and duns. There we go. Nice. This is also done. Okay, train works perfectly. Now I can write optimized model, right? Because now I have the replay buffer. Yeah, now I can write optimized model. So in optimized model, what I need to do is, first I need to sample a batch of transitions from the replay buffer. So let's do that. So here, I will first sample a batch. And if there aren't enough, I have to just go back. So if replay buffer, replay buffer. So if the length of this thing is less than batch size, then I just return because I don't have enough to learn. And otherwise, what I do is I just sample. So I have states, actions, rewards, next states, duns is equal to replay buffer dot sample batch size. Okay. Now first I've sampled, that is done. Now I need to compute the current queue values for the taken actions. So I need to compute QST80, which are the queue values of the actions that are usually taken. And the way we do that is we just do self.policyNet of states. So what I mean is I do state action values is equal to self.policyNet of states. And I need to select the queue value corresponding to the action. So I can use the PyTorch gather function here, and I just go unsqueeze, and I unsqueeze along the last dimension maybe. And then what I need to do is I need to put it all back. So this is just a bunch of PyTorch manipulation. So you get the state action values. Once you get the state action values, you compute the target Q values using the target network, right? So for that, you go with torch no grad as usual because you're not learning anything. And that's a mistake, I guess. Then you compute next state values is equal to self.targetNet next states, and then you take the maximum of these and you find the best. You take the maximum of the first dimension, and so basically for each state you get the maximum. That's what it means. That's what the first dimension part means. Now you have to compute this using the Bellman equation. So if we remember, the Bellman equation was r plus gamma times max of q of next state next action, and right, and yeah. So what you do is you find the expected values. So let's call this expected state action values is equal to, so this is rewards plus self.gamma because you're discounting, and you do next action values, next state values, my bad. There is one small trick that I just realized. But what if the state is 0, right? So here you just do 1 minus duns. Again, you convert it to floats for, yeah. And this, when this is done, give me 1 second. Yeah, and when this is done, you just compute the loss, which is, you already have the loss, which is between the state action values and the expected state action values. That's it. Now, this stuff is just neural network stuff, self.optimizer.0 grad. This sets all the gradient values to none and clears any previously performed values, and then loss backwards computes backprop. Here, one nice idea always is to go torch.nn.utils, clip the gradient norm. So, isn't this, I forgot which is it, but yeah, this is it. So self.policynet.parameters to 1.0. This will prevent exploding gradients. I'm not sure it will be a big problem here, but self.optimizer.step. That's it. And then I do self.steps done, which is on line number 21. I do plus equal to 1. Then, yeah, here, yeah, that's it. Like literally, that's it. So here, one thing is you can write like a progress bar of sorts, but it's not necessary at the moment. So whatever. Wait, no, no. So here you might have, right? Exactly. Yeah. So here you have to, if let's say a good rule of thumb is to just check if the mod is equal to. Now here you need to update the state tick of the target. No, not that. Dot state tick. Actually, I think it's load state tick. And you do this itself. Policynet.state tick. And you can obviously print a nice f string here. Target network updated at steps self.steps done. Yeah, this is your DQN agent. We have train, we've written DQN agent. What else do we need? And then we also wrote our replay buffer. I'm just thinking, we also wrote our thing. Yeah, we have to pre-process. This stuff. Once we pre-process, everything is done. So I'll just put that here. This can just be a function. So this is like pre-process each frame. And the input is going to be a frame. So first thing we need to do, I'll just convert it to, actually I'm not sure about the code here because I rarely try and remember this pre-processing stuff. So let me just quickly, okay, so I found like some code online that did the resampling part, so I just use that. It's fine. I mean, it's none of my business. It doesn't have anything to do with the actual training stuff. So now here the final part is how do we write the training? So how do you actually set up the training part, right? Like because we've done most of the hard work. Now it's just we have to put everything together. So first we start off with counting the total number of frames. Then let's have a list of episode rewards. Oops. Then yeah, so now we need to collect a bunch of stuff to fill the replay buffer. So for that, what we do is we do state raw because it's like what do you call it? We're not pre-processing them directly into torch.floats, and then we do state processed. I just want to check if this works. I already did by the behind the scenes, so a little bit of stuff that I did behind the scenes, not too much. State raw, then right. I'm just thinking what else do I need. So first what I do is I take these frames, I stack all these frames in a queue, and I think I just go the processed frame and I just multiply it with the stack size, and then obviously I just set max length equal to stack size, right? So and then I will convert it to an array first. What should I name this? Current stack state. So this is 5 basically, and I'm filling up stuff into 5. So np.array of stacked frames dq, and d type is equal to np.uint8. Nice. Next, I need to go for I in range, initial collect steps. Action, I just sample from the environment action space. Sample is the right thing, yes. Then I go next frame, raw. Then I get revolved, I get terminated, I get truncated. This is from the docs that I was reading. N.step action. Then I have done is equal to terminated or truncated, depending on whatever you want. And then next frame pre-processed is equal to pre-processed frame of next frame raw. Done. And then you just add this to the stack frame. And the same thing, you just update it. np dot. Now, I just realized that a bunch of the stuff I was talking about for the last 15-20 minutes, the audio completely cut out. So I'll just explain the code. Yeah, it just pretty much sucks, but it's okay. So I think like I was here, like somewhere over here, where you just have the replay buffer. You add the current state, the action, the clip reward, and the next state to the replay buffer. And then once you're done, what happens is you just add the number of frames so that you get to around like 50,000, whatever we set. Then yeah. So another thing is next when you're training, what we do is we start. We go through all the episodes, we reset environment, we pre-process the frames, and then we send in the frames into the queue and initialize the episode reward, etc., etc. And then what we do first is we take an action, select action, perform the action, and then if we're done, then it's over. Otherwise, we just add the reward, and then we pre-process the next frame, and so on and so forth. We clip the reward. We push the next SAR/SA to the replay buffer, and we just keep doing that until we're done. And we just keep appending rewards and average over the last 100 episodes to just see if we're learning over the long run, and then that's it. So this should like run pretty well, is what I'm thinking. I was just checking, thankfully, that it works. And yeah, so we have this environment. We have 9 actions. So first, what it's going to do is it's just going to go here and start filling the replay buffer. And unless I've messed up something, that should work. And yeah, now we just wait basically. I paused training. I paused this whole process because I realized I did not actually print any progress for this. So now I just wrote a bunch of lines of code to print progress, and now it should be much more verbose. So now you can see that it's doing some stuff, whereas previously it was like just empty. So now it should be much more verbose. So like every 10,000 steps basically, and that's what I've written here. I like print out a message, and yeah, and then maybe I write another message here. Print initial experience has been collected. Let's say collection finished or something, and let's output the replay buffer size. This should be like exactly 50,000. So length of replay buffer. Yeah, and then we can just write main training loop. So yeah, it's filling up frames 50,000, and now it's going to start collecting rewards. Usually in reinforcement time, it's not going to be immediate. So while the training is going to start now, rewards might come only over after 200 episodes or something like that. So we might have to wait, but obviously I'm not going to wait all the while. I'm going to stop recording here, and I'm going to maybe add, hopefully if all the hyperparameters, everything turns out well, I'm going to append a video of gameplay to this. So, but this is how you write the code for this, and in general, the point of the video was given an academic paper, how do you just go about implementing everything and writing code, etc., etc. So this is what you do, this is how basic academic research is done, and yeah, so that's that. I will hopefully append a nice video of gameplay. This should work. I mean, like I'm hoping for training to start, but obviously I've written this statement after the code started running, so I'm hoping that one of these will show up soon. Let's see if we can find out where the cursor is. Usually on Colab you can see exactly where and which part of the code is running. Yes, see. So now there's no reward at all, and like you can see the epsilon value, total number of frames, 50,000 plus, so 832 frames have been seen in the first episode, and then maybe it just got to just reset itself, because reset is one of the action values that you can take. That's not the right terminology, one of the actions that you can take. So you'll just do this for like 500 more times, and at the end you'll see a pretty nice reward. In general, this is how you would do stuff, and that is it. I will end with this now, and I will add a video of nice gameplay at the end of this.